Our initial analysis of magnetohydrodynamics established how passing high-amperage electrical currents through raw seawater creates the kinetic thrust required for propellantless ocean transit. However, the true apex of this physics discipline is not found on the exterior of the hull, but deep within the vessel's internal propulsion bays. In 2026, the world's leading marine reinsurance syndicates and sovereign logistics funds are funding a massive second wave of research into closed-loop magnetohydrodynamic fluid systems. This advanced layer of engineering moves away from corrosive open seawater and transitions towards sealed, ultra-high-density liquid metals and supercritical fluids running through continuous electromagnetic loops. This internal power architecture is completely redefining the operational lifespan and asset valuation of transoceanic cargo fleets, turning the interior of modern transport ships into highly profitable, silent thermodynamic power plants. The foundational science of this closed-loop evolution relies on the fluid mechanics and electrical conductivity of liquid metal alloys, specifically eutectic gallium-indium, or superheated supercritical carbon dioxide seeded with cesium particles. Unlike seawater, which suffers from low electrical conductivity and high chemical volatility, a sealed loop of liquid metal offers a massive density of free electrons, allowing the system to interact with applied magnetic fields at an unprecedented kinetic scale. By utilizing high-output compact fission systems or advanced thermal batteries to heat this conductive fluid, engineers create a high-pressure, high-velocity internal stream. As this superheated liquid metal forces its way through an array of static superconducting magnets, it reverses the traditional MHD propulsion mechanism. Instead of using electricity to pump fluid, the kinetic movement of the fluid through the magnetic field generates massive currents of direct current electricity with zero mechanical turbines or spinning alternators. For the multi-billion-dollar global maritime insurance and underwriting sectors, this solid-state power generation represents a total elimination of catastrophic operational risk. In legacy shipping, the mechanical conversion of heat into movement via steam turbines, gearboxes, and crankshafts introduces thousands of points of frictional failure, accounting for over 60% of all mid-ocean maritime insurance claims. A closed-loop magnetohydrodynamic energy generator, having completely eliminated moving mechanical parts, experiences virtually no structural wear or material fatigue over decades of continuous operation. This unprecedented reliability allows institutional infrastructure funds to secure massive reductions in reinsurance premiums, permanently altering the long-term capital allocation models for intercontinental shipping fleets and giving MHD-equipped conglomerates an unassailable financial advantage. However, containing and governing a closed-loop liquid metal system under continuous electromagnetic stress introduces brutal magnetohydrodynamic boundary layer constraints. When a highly conductive liquid metal travels through a narrow conduit wrapped in ultra-powerful Tesla-grade magnets, it experiences a phenomenon known as the Hartmann effect. The fluid near the center of the pipe accelerates rapidly, while the fluid interacting with the inner walls of the containment conduit experiences severe electromagnetic drag, generating extreme localized shear stress and thermal hotspots. To prevent the containment walls from suffering immediate erosive delamination, metallurgical engineers are lining the fluid channels with specialized monocrystalline silicon carbide and hafnium carbide ceramics, which possess the extreme dielectric strength and thermal conductivity required to stabilize the turbulent fluid boundary layers. This second chapter of magnetohydrodynamic engineering demonstrates that the future of global logistics capital is being decided within the deepest atomic layers of fluid dynamics. Sovereign trade networks are no longer treating ships as mere physical containers, but as self-sustaining, closed-loop thermodynamic systems governed entirely by electromagnetic force vectors. The financial institutions currently capitalizing this closed-loop transformation are effectively decoupling international commerce from the mechanical limitations of the industrial age. The long-term survival of high-tier logistics portfolios now depends entirely on mastering the internal friction and electrical properties of superheated fluids, proving that the ultimate foundation of global trade dominance remains bound to the absolute laws of magnetohydrodynamics and solid-state physics.